Welcome Year 12 to the first class for Chapter 7. Now dealing with Chapter 7. Before we do that, we're going to do a little bit of revision. I'll come here and just show the outline. We're dealing with trig functions, and you can see we've got 5 exercises in Chapter 7 before we head towards our assessment task. Let's see how we go. Just revising what we've already covered in Year 11. Shapes of graphs. We can see, looking at this graph here, there's your basic sine graph for one cycle. There's a cosine graph for one cycle. There's a tan graph for one cycle, although we don't often write it like that. We often write it like this. And if you go out to 2 pi, it looks like that. And you've got some asymptotes, obviously. And we can see our cosec, sec and cot graphs that we've looked at recently, not used anywhere near as often as the other ones. Now, the first exercise is dealing with small angle approximations. Now, it's really important that you notice for small angles, we are talking that you must be in radians. If you're not in radians, this method doesn't work. Now, the first part that we're going to focus on is this part here. Sine x approaches x. So let's actually have a look and see what that actually means. Let's come over to Desmos, and you can see I've got y equals sine x graphed. And you can see along my y-axis I'm going up in 0.1s, and along the x-axis I'm going out in pi on 3s. What I'm actually going to do is I'm going to change the way my x-axis is read. I don't want to go out in pi on 3. I want to go out in increments of 1 because I'm going to write my radians as whole numbers. Remember, pi is 3.14. So when I look at this now, when you go through your graph, you can see at that point there is the point pi comma 0, and you can see that when you look along the x-axis it's a little bit bigger than 3 because remember pi is 3.14. So now I've got the x-axis measuring in radians. The y-axis is measuring in my units. I want to now really zoom in. Let's really zoom in now. So I'm going in really close. And this is a sine graph. Let's get in really close. And you can see I am getting super close. And as I get close, let's actually have a look at something. Now, I've got in super close. I want to focus on, see if I can get the point to come up. That point there. You can see that point there. That's what I want to focus on. Now, what's its x value? Actually, as we move along, anywhere along here, let's have a look at the x value compared to the y value. Can you see that the x value and the y value are pretty much almost the same? Pretty much almost the same. Pretty much almost the same. As I go along, pretty much the same. Not quite, but pretty close if you look at it. Let's zoom out a little bit. Let's come back out. Let's come back out. Let's come back out. Let's come to, well, let's come out even further. Let's come right out now. Let's come out to this point here. Okay, so we're on here. Now, have a look at the x value compared to the y value. Are they close? They are very close. Are they close? They are very close. So what does that actually mean? Well, let's go back to our graph, to our diagram. What it actually means is this. When you have a sine graph, if you choose a point that's very close to the origin and you look at its x value and you look at its y value, they're almost the same. And what we need to understand is that the x value is the value that's measured in radians, and the y value is, in this case, sine of x. So that means when you put in an x value, the answer is very close to the y value or the sine of x value. And that's what this statement is saying, that the sine of x value and the x value are really close to each other when your angle is small. Let's actually have a look at the tan graph here. This is saying that the tan x value, which is the y value, is close to the x value when you have a small angle. Let's go back to our graph. Let's now look at a tan graph. There's our tan graph. Let's zoom back out a bit, and you can see the tan graph, and I haven't put the asymptotes on, but you can see there's the basic shape, and it's very symmetrical. As I zoom in, let's actually have a look at points on the curve. What do you notice about the x value and the y value? Remember, the x value is the radian, the y value is the sine of that radian. They're very close to each other. So what we're saying is, for a tan graph, when x is small, the answer is almost the same as the y value. When you're dealing with a cos graph, it's totally different. If I go to a cos graph, let's come over here to a cos graph. If I deal with a cos graph, when you've got a really small angle, when the x value gets really small, your y answer is getting closer and closer and closer to 1. So, what does that actually mean? It means it quite a lot. It means that we need to understand for sine and tan, if the angle is a small angle and we are in radians, if I said something like this, if I said this, whoops, let's get out of that one. If I said something like this, the sine of 0.1 radians, I'm in radians mode, what's it equal to? Well, I could say it's approximately equal to 0.1, because I know that if the angle is really small, the answer is very close to being what the angle was. If I did the sine of 0.062, that's a really small number, then the answer is very close to 0.062. You can verify all this on your calculator. If I did the tan of a really tiny angle, let's say 0.8, then the answer is close to 0.8. If I did the cos of a small angle, the answer is very close to 1, because it's the odd one out, cos is. Now, we can go one step further. I'm going to erase all of that there. We can go one step further, and we can actually say something like this. We can say the sine of x, we know the sine of x is very close to x, and x over x is 1. And that only works if x is really small. If tan of x is close to x, that's what it says there. Tan of x is close to x, that's similar to x over x, and x over x equals 1 if x is really small. Let's see if we can make sense of this. Looking in at x equals, if x is a small angle, evaluate the limit as x approaches 0 of sine 5x over x. That's our first example. So that equals the limit as x approaches 0, that's still there, of the 5x. Well, actually, let's rewrite that slightly differently. Well, no, we will do that. And there's several ways you can do this, that's why I need to be careful. So we will write the limit as x approaches 0 of, what's the sine of 5x going to be close to if x is small? It's going to be close to 5x, because what's the angle? The angle's 5x. If x is small, 5x is small, so the answer is very close to 5x. 5x over x, the x's cancel, so the answer is going to be very close to 5. Let's go to example number 2. Use small angle approximations to give an approximate value to the sine of 1 degree. Now, remember, I don't want to be in degrees. I want to be in radians. How do you convert from degrees to radians? You times by pi over 180. So this is the same as 1 times pi over 180. Now, I'm going to put pi over 180 into my calculator just to see what it is as a decimal. So I've got my calculator here, and I'm putting in pi over 180. As a decimal, it's 0.017 approximately. So I don't really need to write that, but I do need to understand that pi over 180 is small. So the answer is very close to pi over 180. That's what we're going to say it's close to, or 0.017. Now, remember, let's come back up here, the odd one out was cos. For the second question, it says the cos of a really small angle. Now it needs to be in radians, so the cos of 1 degree is pi on 180, which is a really tiny number because we know pi on 180 is 0.017. That answer will be close to 1. That's what we're saying it's approximately equal to. Part C. The tan of 1 degree is the tan of pi on 180, which we know is a really tiny number. So the answer is very close to the actual tiny number. Now question 3 says to find the diameter of the Sun to the nearest kilometre if its distance from the Earth is 149 million kilometres and it creates an angle of 31 minutes at the Earth. So here's the Earth, here's the Sun, and to go from centre to centre, that would be 149 million kilometres. If I go to the outside and to the outside, the angle that's created is, I might just erase that back a little, oops, now I've wiped out the whole Sun, let's put it back, just put it a little bit neater, it's better. Now that would become a right angle, and what I get is the angle that I'm dealing with is 31 minutes. Now half of 31 minutes is 15 minutes and 30 seconds. So that would be half of the angle that's created at the Earth. Remember, the word subtends just means created. So this side would be 15 degrees and 30 minutes as well. Add those two together and they add up to 31 minutes. Now if I look at my triangle here, whoop, don't want that one. Let's go for a narrower one. If I look at this triangle here, I can see that I've got a 15 minute and 30 second. The hypotenuse is 149 million, and I want to find the radius of the Sun. So that would be opposite over hypotenuse, which is a sine question. So the sine of 15 degrees and 30 minutes equals R over 149 million. R equals 149 million times the sine of 0 degrees, 15 minutes and 30 seconds. Whoops, I missed a 30 back on that other one, didn't I? Put that into your calculator, and I'll put that in now. 149 followed by 6 zeros times the sine of 0 degrees, 15 minutes, 30 seconds equals 671,804.04, that'll do, to the nearest whole number. So the diameter equals twice the radius, which equals 2 times that, which is 1343,608 kilometres. So it's about 1.3 million kilometres, which is rather large. Well, it's now time for you to try some questions. Have some fun. Bye for now.